Oh, it's a 2160, lecture 19, the nonlinear functional approximation. This is the first lecture on part 4, machine learning and the nonlinear system modeling. So, talking about the nonlinear dynamical systems, well, any kind of practical systems are nonlinear to some extent. And so far, we somehow abbreviated or ignored or approximating nonlinearity to some linear dynamical systems. But that's actually very well developed and powerful theoretical foundations existing for linear systems, but we have to go into the nonlinear dynamical systems. So shown here, just a simple mass spring damper systems. Spring may be nonlinear. This is a hard spring going down. It's a soft spring. And the dry friction is very nasty nonlinearity, having a very pronounced static and dynamic frictions. So many systems are nonlinear in many ways. There are several ways of approaches to nonlinear dynamical system representation and tuning, identification, and learning. One way is I would call the hybrid linear nonlinear modeling. And then the concept is that putting all nonlinear elements involved in the system to either input side or output side, we can split the original nonlinear dynamical systems into a linear and a nonlinear systems. And the linear systems, we can well deal with the dynamics. So, first case, it's called the Hammerstein model. Input is immediately going to some nonlinear algebraic map, so some static and nonlinear function. Okay, the output is fed to linear dynamical systems. We have done this in system ID and estimations and others, right? Wiener model is opposite. First, the input UT is going to linear dynamical systems, and the output is fed into a nonlinear algebraic map, and then creates the output YT. Yet, to my knowledge, a Hammerstein model is more popular, and then we see this in many cases. This is nothing but the applications and approximation, I would say, because nonlinear elements are partly involved in the springs and partly involved in the, say, friction models. They are all, connected together. So usually, each nonlinear element cannot be actually, lumped together. But suppose we can do that, then we can split the model in this way. One part in mostly focusing on the nonlinearity, but we put the dynamics aside. We just we look at the pure algebraic input to output nonlinearity. They're followed by the linear dynamic model, which can be done in many ways. Perhaps some of you who are more familiar with the nonlinear controls may think about the so-called, the method, the so-called describing functions. They are actually, the particular ways of dealing with the nonlinear functions in a linear way. And the basic concept is that even though nonlinear elements are scattered around, but we approximately put them together into one nonlinear function, and we look at the first, most dominant frequency component to obtain the frequency transfer function, which does approximate to some nonlinear function in a systematic manner. So this is one method. The other method is somehow we use the time delay outside of an algebraic map. So the first case is that the incoming input UT is basically tapped to produce not only UT, but UT minus 1, UT minus 2, UT minus M. All these are fed into a nonlinear algebraic map. So in somehow dynamics are created outside of this nonlinear algebraic map. And this algebraic map may be created with use of a neural net and other technique like a radial-based function, which we study today. And basically, this particular part has no dynamics in it, but it can actually find a way, finding a relationship among these, and then best produce the YT as a prediction. Another framework is basically use of feedback, and then in the feedback loop we put the time delay. So I know some input comes in, the first algebraic map going there, but the YT is also fed back to this with the single time delay, and then used as a part of the input. So this is going around. So this one is to create the infinite horizon. The kind of dynamic behavior can be captured by this kind of modeling. Well, in fact, the time delay is used, in the forward pass. It's the technique is called the directed cyclic graph that can capture some of the dynamics, but I know not well used in the systems and control on the literature. So we focus on these methods. Yeah, interestingly, including all these neural nets. Oh, and then actually this one is so-called the recurrent network, being a very powerful tool for recognizing the time sequence data, such as including voice recognition. So that's actually recurrent network. So all of these actually I showed you include some nonlinear algebraic map. So nonlinear algebraic map is one of the key building block in the nonlinear system modeling. So today we focus on this nonlinear algebraic map, and we introduce a particular class of techniques in doing this. So nonlinear algebraic map, simple case, input X versus output Y, some ugly nonlinear function like this. And most of the techniques that are being used is to expand a nonlinear function to a series of basis functions. So now here, basis function is GKX, and then typically linear combinations of these with the proper number of basis functions, and tuning this parameters weight and alpha k properly, we can approximate the given nonlinear function y of x. And this is not surprising because the Fourier series expansion. And then if you use the sine cosine functions for this GK, that's nothing but the Fourier series expansion. We know that then as m tends to infinity, we can actually represent the class of nonlinear functions very exactly. You can also use the polynomial like x1, x1 squared, that kind of polynomial functions to represent, to form a group of basis functions. And if that's the case, that's a Volterra series expansion. Volterra series expansion. Some examples are shown here. The first three terms are linear, right? Alpha 1, x1, alpha 2, x2. But here's the cross product, x1, x2, and then x1 squared, x2 squares. This term's going forever. Okay, that's a Volterra series expansion. I know that the Professor Ian Hunter, his doctoral thesis was on the Volterra series expansion, and he's been one of the major contributors to this technique. Now, more recent, the techniques are involved in the so-called locally tunable basis functions. So these actually, Fourier transform, and then actually Volterra series expansion. the basis functions, basically, this is to cover the entire range of x. However, this locally tunable basis functions is mostly focusing on the specific regions. So for instance, this bell-shaped functions, it is to cover x from a certain value to a certain value. And sometimes this one extend infinite, but I know major focus is to contribute in the specific regions. And we put together many of these basis of functions, building block of functions, and basically superimpose these to approximate the given functions. Okay, so locally tunable basis function can capture local features of a nonlinear function. And key point here, if you use just global basis function like a sine function or polynomials, it is actually hard to capture some of the local features. Shown here is one example, say to detect the earthquake, seismic signals to record it, right? This one is actually the ground is not moving all the time; it's mostly stationary. But at the time of earthquake, it is to shake, right? So if you take a bunch of data and then actually expand to a Fourier series, basically product between this one and this kind of particular signals is to be integrated for the entire X span. But so such local features like this will be just integrated out, averaged out. So we cannot actually capture some of the unique signals here, right? But instead, if you have some locally tunable basis functions, we can capture this. Yeah, one of particular, particularly interesting functions is called the wavelet, which, if I have time, I'll explain that at the end. This is to capture some of the spatial temporal functions, and that has this particular, kind of a short oscillation type of wave patterns, and use that collection of these wave patterns as the basis functions. More actually, widely used function is so-called radial basis functions, of which we will discuss further today. There's something like the bell-shaped ones. Okay. Interestingly, in a neural net, it's actually sitting somewhere between the global and then the local. It is global in the sense that it can, basically, theoretically, in principle, it can receive all the signals coming from, all variables, but it is actually mapped to the output with some specific output function, which is actually, in most cases, local, or just a partial of the output. So it is to zoom in the particular part. Anyway, so this is the one of the interesting contrast between somewhat well-established classical methods versus more recent method. Radio-based functions, wavelets, and neural nets are basically more tuned to specific local features. Okay, now radio-based functions are one of the most widely used local basis functions in control, the machine learning. And in this part 4 of this course, you will see the radio basis functions repeatedly. One is actually Carnot functions, Gaussian processes, Kaufman observables. You have no ideas about this, but you actually use this radio basis functions repeatedly. So it's a very important tools that I hope everyone to master. So local basis functions are powerful tools for capturing local features and then representing a nonlinear function with locally tunable resolutions and accuracy. Radial basis function is actually, include many, functions, but all of them have one particular feature that is actually, as the name says, it is symmetric about some center point. So it is a function so only depending on the distance between some center point and the input point, to say x. This is the n-dimensional input space. And there's actually for each radial basis function has its own center point, the center coordinate, gamma k. And you evaluate the distance between the center point and your point of interest x. And this function is only depends on this the distance. So all the points along this circles having an equal distance to the center takes the same value. So that says it's actually the function is symmetric about the center line sitting here. Okay, and we put together many of them. Now this actually distance is somehow weighted, scaled, I would say. Distance Rk is scaled with the so-called dilation parameter beta, and here's the actual definition. So this is the the net the distance divided by beta k. This is dilation parameter, and then that's the actually weighted distance from the center, and then that is used for evaluating this function. So if beta is small, it is actually x minus gamma. This distance, even real distance is short, but if this one is small, it turns out to be a large value. So that means a little bit out, away from the center point, it goes down quickly. And then if beta is actually large, it is actually more widely spread like this. Okay. Now, radial basis functions, as I said, the many functions involved, but in one particular form, which is most widely used, is a Gaussian bell. So exponential minus r that weighted the distance square. Okay, we put many of these radial basis functions with many center points distributed in the input space, n-dimensional x space. Okay, and actually a linear combination of these is to approximate given nonlinear function g naught. Okay, so so the question is that approximation, then you concerned about how accurate is accurate, right? And we have to pick the right functions, right basis functions having a proper properties, so that we can actually approximate the broad class of nonlinear functions, to certain accuracy. And here's the actually some supporting underpinning theory, mathematical foundation. It's called the function approximation theorem. So for a class of basis functions, there are many of them, and actually that includes neural net functions, including those can approximate a broad class of nonlinear functions to any accuracy. What this means is that you provide any small positive number epsilon, okay, and then given for any arbitrary epsilon, there exists a finite integer m such that this approximation and then this real nonlinear function, the distance is basically bounded by epsilon. So as you provide the much smaller epsilon, perhaps you need more functions to approximate m. But for given epsilon, there exists a finite m that makes a difference, smaller than this given epsilon. For all x and the defined area, that's actually a compact subset. So yeah, this is just a key point of the mathematical theory, being studied by many people for a long time, including Kolmogorov, who did one of the very important contribution to this field. And as I said, some neural net, multi-layered neural nets, actually 3-layered neural nets having the particular output functions, can satisfy this function approximation theorem, so that the neural net it's actually a useful building block to approximate any nonlinear function. Although this theory is actually to encourage us to use this, however, it doesn't say where you place these building block basis functions, and how if you use the radial basis functions with Gaussian Bell functions, it comes with this particular parameters, beta and gamma, center point and the dilation parameters. It does not say, the theory does not say how to choose these, but it says that there exists a finite m. So just actually a peace of mind, but doesn't help us in any ways to construct such a function to approximate it. So in the rest of the part, we have to do it in a constructive way. Okay. So tuning of a radial basis function network and the system identification or machine learning context, we're not given the nonlinear function g of net, g naught, but instead we are given a input to output the data such as the xi, yi pair, I equal y1 to n. So what we need to do is to fit the set of series of radial basis functions so that it can, the set can approximate the input to output data appropriately. So there are two actually methods. One easy, the other is a little hard. First one is what I call the non-adaptive grid method. This one is straightforward in a sense, but it's not so much efficient. So we need to put together the series of radial basis functions in this way, right? So easy way is just let's actually put these radial basis functions at every grid and the input space. So you can actually split the x1 axis into say hundreds, and the x2 axis 100. So our grids maybe 10,000, and you use the 10,000 radial basis functions to cover the space. Well, oftentimes we don't need a 100. Maybe 10, 20 radial functions are typically used. But we place these at every grid like this, right? So so the center point gamma k is basically these grid points. Okay. Now dilation parameter beta 2 are actually we somehow predetermined. We pick the value and then actually see what happens. Okay. So the emphasis is that say somehow beta and gamma are predetermined. And rest of the part is basically alpha is to be determined. Say this guy is determined to best approximate this input output the data set. So yeah, originally radial basis function is actually having 3 parameters RK, beta k, and gamma k, but the beta k and gamma k are basically fixed in some ways. So beta k, gamma k is basically distance r is nothing but a function of x alone. So let's write this radial-based function as gk of x alone. So this is nothing but just output y is actually created with this actually a summation of these terms, right? So what we need to do is to determine alpha 1 to alpha m so that actually it can best approximate to this. So that's an easy program. So what we need to do is go back to the simple prediction error model, that formulation, so real systems producing a yi, and in response to xi, and the model is to respond to this nxi, yi hat, and that is actually depends on the parameters and being used. So in this case, yi, yxi hat, squared sum of the squared is to be minimized, and the parameter that is to provide this is actually an optimal parameters. And here, prediction is nothing but just a linear regression, right? So we basically treat all these actually radial-based function, the G1 to the Gm, as the regressor, putting this one in this way, and the weights alpha 1 to alpha m to be the parameters to estimate the parameter vectors. And this one is nothing but the linear regression like this. So this is a very easy, simple program. So the solution is given by minimizing this with this is basically given by this least square estimate solutions, right? Let's look inside of it. Well, first of all, the parameters to optimize is alpha 1 to alpha m, so putting a hat over here. Now, what is the regressor? Regressor is actually G1 to Gm. So placing these regressors into this form, this one is phi, regressor phi. So we need to put the back-to-back phi and phi transpose. Right, phi and phi transpose. And then actually taking summation and take the inverse of it. We assume that the data is actually rich enough to span the m-dimensional space, so that this matrix is to be invertible. And this side, the phi and the y, the product between the two, can produce this term, right? So this simple least square estimate can be computed in real time. So it's so quick to compute, right? And this simple linearity has been exploited for actually constructing some of the adaptive controls or learning control the systems where this linear regression is incorporated into, in the case of adaptive control, typically they use Lyapunov functions, and actually state has been extended to include these parameters and alpha 1 to alpha m to be additional states, and then actually that alpha 2 having some dynamics, and then that can be incorporated into Lyapunov functions. And we can actually guarantee that the system can adapt it to any unknown situations, and not only driving the state to desired values, but also the actually some of the unknown nonlinear function that can be identified by a collection of this radial-based functions that represent the output weights alpha 1 to alpha m that can be estimated together. So that the kind of thing has been done. So I know this this method, radial basis function with the grid method, is very simple and being used quite extensively. But I know the problem with this, right? This, however, requires offline tuning of dilation parameters and the grid points. This one is really, question of grid points. An obvious drawback is the curse of dimensionality. The curse of dimensionality, right? So back to this. So I just showed a two-dimensional, an input case, x1, x2. But suppose you have, say, 5 dimensional input space. So you have to fill this tile in a 5-dimensional wall, right, or floor. That's a lot. Even though you have divide the one axis into, say, 10 segments, and each covered by single radial basis functions. So the 10 radial basis functions per axis, 10 to the 5th order of radial functions are needed. So surely this method does not work. The grid method does not work for those actually cases having a high dimensional input space, right? So that's an obvious actually drawback of this method. Okay, so what do you do? Well, we should be able to think about something. Back to grid, we don't use the grid. Instead, we allocate radial basis functions more effectively where needed. So this is called the data adaptable method. So depending on the data, you have more data here or very sparse data here, or this particular part, you have a very actually, changeable waveforms, but you need to capture. So obviously, spatial frequency here is very low, but a spatial frequency here is high, right? Some part having more data, some part is not actually much the data, so forth. So data provide some kind of properties. So why not actually tuning these radial basis function parameters to meet such actually specific features of the nonlinear function. So the grid method uses uniform dilation parameters beta, right? That's actually not effective. So not only just the use of abandoning the grid based allocation, we have to use the limited number of radial basis functions more effectively by allocating the center points at those areas needed. And also, we tune the dilation parameter beta k to be more effective. So nonlinear functions may have diverse spatial frequencies depending on the regions of the functions, right? Higher resolutions may be needed in a particular regions, while lower resolution is just okay, for other regions. It does not actually contribute to the total performance. Okay, maybe square, the square fit may not actually be influenced by those very scant points. So if the density of radial basis functions and the dilation parameters can be tuned to specific local properties, and also needs some particular point you really want to capture this, and you don't care this part, but you really want to capture the signals here more with high fidelity. So that's actually needs. So depending on the needs, a limited number of radial basis functions can be used effectively for approximating a given function relationship. So here, the low resolution part, we can use the sparse radial basis functions, and as you can see here, it's very gentle. That means actually large dilations, and distance between the adjacent radial basis functions are kind of long, but each function can cover the larger areas, maybe overlap in some way like this. On the other hand, this particular part, the high resolutions are needed, and then we like to really capture this. So we have more sharply tuned, many of the little functions are used in here. So how we can really allocate this and how we can really tune gamma and the beta to meet such requirements. So data adaptable method. So depending on the spatial frequencies of a nonlinear function, G not X, this is actually given nonlinear functions, okay? And the required accuracy, approximation accuracy, the density of radial basis functions and the direction parameters can be adjusted. So that's what I said here. And then now we like to adjust the gamma and the beta, okay? So the challenge is that the direction beta k and then center point to gamma k are non-linearly involved in each radial basis function, right? So this is the inside of exponential, and we like to tune beta and then gamma, right? So that's actually no longer linear least square linear regression program, but the non-linear involved. So here we need some algorithms to make that happen. And also I have to say that in principle, the three parameters, alpha, beta, gamma, alpha is the one that's actually a linear weight for creating this guy, right? Creating these actually weights. That's actually, linearly involved in here. And the beta and the gamma is not, okay? Beta and the gamma is not. But in principle, three parameters, alpha, beta, gamma, should be optimized simultaneously to best fit the given data set. But in fact, it is very difficult. So a practical approach is actually a sequential tuning. So we first tune gamma, center points are determined, followed by direction parameter beta k, and finally this weight alpha k. So step one, placement of the center points. Step two, determination of the direction of alpha beta k based on the variance of nearby data points. And actually step three is the least square estimate. So that is the procedure that we take. So data adaptable method. Step one. This one is center point placement, right? So more radial basis functions are to be placed in the area having a higher density of data points. So I know, so somewhere Wyoming or North Dakota, and not much actually, populations here, right? So on the other hand, going to some counties having a higher population over here, we need to have more actually, radial basis functions to represent that, right? So, just looking at that kind of map, we like to locate the, limited number of radial basis functions more effectively to reflect the population distributions, right here, okay? So, suppose that a given number of radial basis function M are to be placed in an input space of capital N data points, x1, x2, x small dots in here, right? And how can we find the M center points so that the density of the data points is approximately proportional to the density of the center points? Okay, so those are all actually, complex problem. This is one of the basic, AI programs. So machine learning program. This problem can be solved as a clustering program or vector quantization program. So, we introduce one method and then, let's solve this program. So, given our n input data points, x1 to x capital N, right? And then you specify the number of radial basis functions, M. So you said that, my computational resource is to compute the 1,000 radial basis functions, nothing more, okay? Tell me the best way to place my 1000 radial basis functions in the input space, say some dimensions, right? So that's a problem. You need to provide the initial location of M center points. Let me denote it as actually, I know, round 1, round 2, round 3. We provide round 0 distributions of first center point gamma 1 to mth center point radial basis function to center point gamma m, given this. So now see how we can actually determine these. So, we use algorithms called k-means clustering algorithms. It's not the k-nearest neighborhood algorithms, okay? K-means clustering algorithms. So step 1, we set the iteration index L equal 1, okay? Then, no, I had to say the L equals 0. I'm starting with the L equals 0, otherwise it doesn't go. Okay, starting at L equals 0, and then, we are given actually, gamma 1, 0, gamma 2, 0, gamma m 0, right? Initial conditions been given. Okay. Then what you need to do is just as shown in this, plot. So we are given gamma 1 and gamma 2 are here. Let's say 2 center points existing here. We look at the order, the data points, and actually find which, of these two are the closest to this, xi. So in this case, I'm comparing this distance, versus this distance, and this distance is short. So this one belongs to, this center point, and then this one, comparing this distance, and this one shorter. So this sample point j, sample point, data point xj belongs to gamma 2, sample point. Okay, so after you do this for all the data points 1 to n, all the data points have some address. This one belongs to this, this one belongs to this, right? So if you collect the results, each center point has some neighbor points, x1, x3, x5, or whatever. Okay, and then this actually center point has a group of neighbor points, x something. Okay, so now in step two, look at the each center point. The center points has these data points belonging to this particular center point. Among these data points belonging to the same center point, we recompute these centroid of these points, center of mass, or first order momentum is to be computed. That said, that even though this one is originally center, however, this new center may be a better point to get to actually be closer to this group of points, right? So in step 2, we update the center point from gamma k else to gamma k L plus first. So moving this one here. As you move the center points, maybe this one getting closer to this, and this one moving to the other way. Previously, this guy belongs to this, but that may be different for the new set of center points. This may belongs to other points, other center. This may belongs to other center. So in step 3, we actually repeat this step 1 and step 2 by first increasing the L to L plus 1, and then repeat these 2 steps, looking at every single point in the data points, and then find the closest center point. And then as you change, as you collected all the points belonging to each center point, then recompute the center coordinate themselves. So we repeat that until you see the total metric goes to some the local minimum at least. So metric is something like this. It's called within cluster sum of squares. So first look at these terms. This is actually xi and the gamma jl. So around the L, we have a center point in Rj, and then we compute the square the distance to that the center among all the points belonging to this center. How do you collect the points belonging to this? And we use this membership index. So Qij takes the value of 1 if data point I belongs to cluster J. Okay, so if this guy belongs to cluster J, then this one is non-zero. So this one is to be added to that sum. Okay, else this is 0. So we compute this. This is the kind of an average within cluster sum of squares. So for this improved center points, we measure the average squared the distance, and then we do this for all the center points, which is basically including the other data points. Okay. So now a little bit actually computing things to membership functions. And then let me just explain a little bit more. And then this is to explain how you implement this kind of algorithms and computer code. So we wrote this equation, right? So this is to collect the QI, the data points I that belongs to center point J, right? So we collect this. Qij is a kind of a matrix like this. It is actually M by N dimensional matrix, right? And then as definition said, if data point I belongs to cluster J, then it's 1, okay? So looking at the ith row, which is actually picks the one particular the data point, ith data point. Ith data point has to belong to only one cluster. On this line, it's all 0. Only this jth column, it takes the value of 1. So only one in each row vector. Okay. So that is a kind of a map we create, and then so as you examine this kind of distance, which one to belong to, you basically keep the record in this way, and then actually create this matrix. Now, on the other hand, after you finish this, you look at the each column. What is this? This particular column, jth column, represent what? This one actually jth center point, right? You put the radial basis function at this center point, gamma j. So this jth center point, basically attract several data points. In this case, 3 data points is actually defined to be the closest to this jth center line. Okay. So with that, let's look at the how next point determining dilation beta k, So first of all, we need to recall the properties of dilation parameters, right? So what was that? It was actually to represent how sharply you actually focus on the local properties, right? So large dilation, beta is large, basically, large overlap, smooth curve, and low resolutions, and small dilations and high resolutions, right? Many of them are needed to represent some curves, so we can capture some high spatial frequency waveforms, right? So, how you actually find tune the value of a beta k it is reasonable to look at the density like this, and actually excuse me, distribution of this in terms of maybe variance. So we compute the within cluster variance. So let's look at this guy. This is actually square the distance to the center point, right? For actually a cluster K. Then actually we have to collect the xi that belongs to that in the case cluster alone. So we have to multiply this and to kick out the ones which are not actually involved in this, and that is basically taking a summation along this line. If this one is a case cluster, we have to correct the terms in here to compute the within cluster variance. And so that the variance is basically to give the this dilation parameter beta k. Okay, so this is the technique we can actually apply to many of the problems that we have to deal with. So first, actually, center point followed by the dilation parameters, and then finally we go to least square tuning with respect to alpha. Okay, so I just said that the one item here discussion, is this the right method? What are we really missing in this method? Let's elaborate. Let's think about this in a little bit. So we actually look at the distributions of input data points, right? Then we determine the center points. Then we actually determine the dilation beta. Is this really the right method? Or what is the kind of quiet assumption we're making? When did this method tends to fail? Any challenge?
It doesn't know anything about the length scales of the nonlinear function. Like you could have a lot of data points somewhere, and the nonlinear function could still be very wavy. And it's better to capture that.
Right, exactly, Charles. That's actually, that is a key point. We haven't used any output to the data Y, right? We examine the only input, X, and then look at the X distributions, right? So we just use the half of the information. This actually resembled some of the argument that we did earlier this term. Remember that principal component regression versus partial least square regressions, right? Partial least regression is to look at the correlation between input and output, but a principal component regression characterizes only an input side, right? Input side, and then which one is the most significant, and then we truncate it in insignificant ones without looking at any of the output variables, right? So, in this case too, say looking at the x-axis, and here's the point that the high actually population somewhere in the Philadelphia, and then this one is actually beyond the Pittsburgh, somewhere at the low populations. And then we decide how to actually assign the database functions, the center points. But even though high population county and many points involved, but all of them showing the same output, all purely blue states and all the same output there. You don't need actually high resolution functions, right? So we are quietly assumed or agreed in some way that the high resolution and the high density of input data points basically implies the high spatial high spatial frequency waveforms for the output. That may not be the case, right? So we need to think about the things a little bit more, in depth. And this problem is not easy. It's a hard problem, and more advanced vector quantization, the techniques are needed to find the best way. But so far, this is the very quick approximations of the problem. As you have more data, you tend to capture more signals there. The data points the density. If that implies how important that area is, then actually this method is okay. Yeah, it's okay. So that's actually some of the limitation to this approach. Okay, so let's actually look at some of the yeah. Let me see. Here's the assignment I just released today. So this is the problem set number 5. And this problem set is to cover two problems in subsystem methods. And then one problem is on the radial basis functions. So this is actually problem 3, radial basis functions. And actually due date is actually next Monday. So you have some time, and you discuss this in the group studies on Friday. So yeah, this is a problem of the voice recognitions and 300 data points in the 2-dimensional input space. And then we like to so this is one particular example. The little dots are data points, and there are 300 points in it. And actually, these triangles are the initial locations of center points where radial basis functions are to be placed. Oh, excuse me, this is the final result. Okay, so let's look at this radial basis functions. And the original location was this point. You can see here this point, the starting point, and that actually a k-mean cluster algorithms, starting with the initial guesswork of the initial center points, and repeat the 2 steps back and forth, right? First step is looking at every point which cluster is the closest. So we actually put the cluster for this, and then actually within cluster zeroth order moment or center point is computed, and then that push the initial point to this little different point. And the repeating process, it's moving around this line and arrive at this. So, all actual points arrive at this one traveled from here, from here to here. This one traveled from here to here. This one too traveled a lot from somewhere here to here. And then at the end, it settled down to the shortest weighted distance. And then you determine the center points. And then all the data points belonging to this center points are to be computed for dilation parameter beta, and that the dilation parameter beta is to determine this radius, right? So this is actually more sparse, and then this one is more actually high density, so a little bit shorter distance. And what this may be the smallest circles, smallest beta, because of the high populations involved here. So this kind of treatment can be done. So the question is that we provided the new data set, and you implement the k-mean clustering algorithms discussed today, and then classifying the n points of 2-dimensional input data into m clusters. Okay, so you start with the m equal 9 radial basis functions, and after you download the data, you can actually find it. You start with the just in a grid point method, m equal 9, create an equally spaced 3 by 3 grid and a 2-dimensional space, and place the center points of the 9 derivative functions initially at those grid points. So grid point method is used as just initial, in a guesswork. After optimizing the center locations, compute the dilation parameters for each cluster. Plot the result in the same way as the above examples showing it. So I expect that you plot something like this, okay? And please implement this. It's just a few lines of code, so it's easy. And then key thing is that please make that the matrix Q, okay? That is actually membership functions. And that is the way to record your, checking which distance is the shortest and such, okay? And actually, after you determine the alpha and the beta, beta and gamma, then you apply the least squares, to fit it, right? Now, here's the one thing I need to discuss a little bit. To evaluate the validity of the tuned radial function network, another set of data has been uploaded to the 2160 website. So, these data not originally used for tuning on the database functions, but are retained for the purpose of actually testing, evaluating. It's called the validation data. And I think we haven't discussed this validation method yet, but this is important, in machine learning. Always we have to retain some data. We hide such class of the data from the machine learning algorithms, and then let it do tuning without that validation data. And then suddenly you show that the new data and to see how it works, right? So we do that kind of practice in here. So please download the second file and evaluate that, okay? Now, this result highly depends on your choice of number of radial function, and also try out m equal 25 and also m equal 100. See how much actually accuracy you can obtain. Yeah. So any kind of method having some parameters that you need to pick, you need to try out, right? So in this case, m is very important, numbers. So that's one of the assignments. So that's easy, right? That's easy. Yep. Now, just to conclude, this method. So the last item which I used to teach this materials a lot, but I know we just gave up at certain points, and it turns out to be very important. Wavelets. So this is one of the very typical locally tunable basis functions. So wavelets are a collection of brief oscillation functions, something like this. Yeah, boo, and then actually starting with the zero amplitude and increasing and decreasing and fading out. Okay, so there are several sets of well-known wavelets of functions, Maillard, Molet, and Mexican Hat. So several of them. Okay, so each having a specific frequency and actually on the features. So so this is just Maillard's the one frequency component, and other basis functions having a different the frequency. So it's more actually shrunken ones, different frequencies, and more too have a different frequency, a set of different ones. Okay, so yeah, so when each function is convoluted with an unknown signal like this, unknown signals, the correlation between the wavelet in each of the wavelet and the signals reveals that where this kind of features happens in here. So suppose this one is something seismic seismograph. Okay, so that's actually some kind of earthquake vibrations and recorded like this. As I said, the earthquake does not happen all the time, so it is mostly quiet, and suddenly it's actually having some peak and then diluted, right? So if you just use the Fourier transform, you just average out such important features, and so you don't get any trait in that. But if you use the wavelet, this pattern, how much of them involved in which location, you can find that information coming out of it. Yeah, so it's being used for not only earthquake signals but voice recognition and heart rate monitoring, cardiovascular signals. They use this kind of method quite extensively. So that's called wavelet. It's better to memorize this, although the details are not covered here. But I know one of the important techniques, which is to cover both the time axis and actually magnitude axis. So the building block of functions has a location parameters and actually a frequency and magnitude components all in there. And then they use the correlation method to find the correlation between the unknown signals and the building block signals. So you can interpret the signals, actually some particular mode of frequency component did occur, such and such a time, and where that happened, and then what is actually the components involved in that frequency component, and then particular features can be extracted from that. That's wavelet. Okay. So now we have a little bit more time. I'd like to use this to discuss further the subspace method, which is actually involved in the assignment this time. And this particular part is a little tough. So I hope you can survive. So this is the PS number 5. So the first problem is about the whole Kahneman method of system realization. And then that is basically baseline for subsystem method, right? In particular, MOST method. Excuse me, MOST method. So that the goal is to determine system matrix. Matrix is A, B, C, D, X t plus 1 equal A x t plus B u t, right? And y t equals C x t plus D u t, right? First let's look at the the case realization. So we have an impulse response coefficient. Well, in a single input, single output, we have a lowercase g1, g2. But multi input, multi output, capital G0, G1. But I know this is the representation of output to YT in terms of the input convolution with the impulse response, right? So now let's look at this particular input output data. So input is actually 0, 0, and then suddenly 1. And after that, all quiet, 0, 0, 0. So this is actually 0 input response, right? And then the output that you observe is 0, 0 at the time step 2 and 1, and then going down in this way. Okay, so from the above data, first I want you to construct the input-output data matrix in the Hankel matrix form. So you remember that the Hankel matrix, particular form, you put the input in a particular sequence, right? Let me just show. Yeah, so you have U0, oops, U0, U1, U2. So you place these in the input Hankel matrix 0 and K. So the first one is actually U0, so that's actually 0 and a 0. And I know U2 is suddenly 1, right? So let's put it this way. And maybe I should put this guy, and then I'll put the Y0K at the same time. So this is the complete data matrix, right? And so this is the U0, U1, U2, and the next one is actually one time shift here. It's a 0, 1, 0, right? And then 1, 0, 0. Okay. And after that, it's all 0, 0, 0 continues to this in this way, right? So now output side, you are given some data. And first, I think it is actually 0, 0. And then some G0 it comes in. And the next one is 0, G0, G1. And then the G1, G2, and the G3, right? And then actually here, oops, 0, 1, 2. Sorry. And then here G1, G2, G3, and such, right? So you form this kind of the data matrix, and the whole Kalman method, we look at this block, right? And this block is having a very specific, Hungarian metric structure, and all impulse response, G's are involved here. And in this particular part, let's see an H33. Let's denote it H33. This can be decomposed to what? To the product of, controllability, observability matrix and the reachability or controllability matrix, right? So you can actually, put this one into two components, and then by taking the singular value decomposition, this can be, decomposed to something sigma and be transposed, right? So from here, you can find the O and the C, and then an O and the C includes the O in particular. Yeah, this one is a little different, controllability matrix. So let me write this, and we're talking about the system X T plus 1 equal AXT plus BUT, right? And then YT equal CXT plus DUT, right? So, observability matrix includes the C and the A that is arranged in this way, C, and then, A and the C all combined here, right? So once you determine, observability matrix, you can determine C, the same one, from this is, comparability matrix, so you can determine this, vector B. And additional method needed to complete this assignment, but that's actually things you can do to determine the ABCD matrices. Okay, so here's the data, and you can compute the ABCD matrix. Okay, please look at the slide deck, and that's a first lecture on subspace method, and then there's actually important example 18-1, and please look at that particular one. Okay, so at the end you can get the ABCD, from this data, input and output data. Okay, yeah, you can raise any questions at any times. Otherwise, it may be more time consuming later. I just want to make your job easier. Problem 2, at the end, I decided to put this one extra credit problem. It's not mandatory, but I highly recommend you to do that. Yeah. So this is to, really actually look at the subsystem identification, method, MOSP, or, enforce it. And here, what we like to do is, let's actually start with the generating the data, input output data. Okay, and then in order to create the input output data, we first assume that ABCD matrices are given like this. Okay, so for these systems, and then you provide some inputs and then create the output, and then that's actually used for input output data for the purpose of system identifications. So we start with the ABCD, so you know the answer, right? This is the answer. So through a system subsystem method, the system ID, you get this result or equivalent result, and that's actually you have accomplished the goal. Okay, so look at this, C and D matrices. Actually, C is actually first, second, and third, and fourth, and then 1, 2, 3, 4. So this one is basically 2 by 4 matrix, and then B is actually 4 by 2 matrix. So this is actually 2 input and 2 output systems. Okay, multi-input and multi-output. Now let's actually create the data. So in order to do that, you need to provide some input. And I suggest the input to be white noise random sequence of 1,000 points. So in MATLAB, you can create the two-dimensional random sequence data, rand n, and then there's a number of data points and there's dimensions. You can create the n by two actually data points, right? So use this as inputs, and then actually fit it into this systems, and then create the output y. So that's the way to create the the data. Okay. With that data, then we apply the enforced or MOSP algorithms. Well, in the MATLAB, there's actually, of course, a very nice, code. Enforce it. It's already available. So go to MATLAB, system ID, the toolbox. You see a lot of tools there, and then they for some reason they actually like enforce it. So you can use that. A few things that you need to know. You need to specify an approximate system order, right? So in the actually realistic system ID subspace method context, we don't know the system order, but in this case, and we started with the A, so A is actually 4 by 4 matrix, so the system order is 4. So that said, you have to provide some it's called the time horizon K. That's actually dimension, estimated the dimensions when you construct the extended controllability observability matrix. That actually you need to use more than the actual number of state variables. So if system is 4, then K should be 5 or 6 or somewhere there. So you provided that number, and then that's one of the key parameters that you need to play with. Okay, so with that you can actually get the ABCD matrices correspond to the data you have created. Okay, now the question is that when you look at the ABCD, surely they are different from this, and then you scratch your head. Have you done something wrong? So that's actually one point that you need to discuss and elaborate a little bit deeper. So typically, you don't get the ABCD matrices that you have originally used for creating data. The question is why? What do you think? Something wrong you did? Well, you did all right, but you don't get the exactly same ABCD. Then you have to think.
Could it be that the problem could have multiple solutions and we get a different solution which still satisfies the input-output equations, but is not the data that we use to generate it?
Exactly. So remember that the subspace method is heavily related to the system realizations, and then starting with the input-output data set, there are numerous infinite combinations of internal states, right? So states, determining state, state vector is not unique. At least we studied that if you use the non-singular matrix multiplied to contrariability matrix versus reachability matrix, they cancel out. If you put the back to back, they cancel out, right? So multiple solutions exist. So how do you know they obtained the ABCD matrices are correct or not correct? You have to convert it to some form, right? What would you suggest?
We can generate another set of random numbers, pass it through our matrix, see the output, and compare it with the output we get from our realized matrices.
Oh, yeah. Right. That's a good one. That's a good one.
Or you could just put them in transfer function form.
Exactly, John. So that's actually maybe decisive method, right? So from ABCD state representation to transfer function, that's a very straightforward, unique transitions. So you can construct the transfer matrices. This is 2 input, 2 output. So transfer matrices can be created, right? So you can actually compute the 2 sets of ABCD. One is the one that you use for creating data, right? And then one that you obtained after you've gone through enforce it in a method. These two should actually agree, at least cross parameters can be obtained. Yeah, so that's something, right? So it's all you need to think, well, any actually comments on this clarification? Just raise, I'm not clear how you approach this problem. So yeah, enforce it, it's already in the MATLAB, so you can use that. And also MATLAB has pretty good tutorials on that. Yeah. Okay. So this will be interesting, just creating input output data sequence, then you can construct the state, representation, that's quite useful. So I hope everyone and gain some experience, as to how to use this kind of algorithms. Okay, that's it. Oops. When generating a random white noise, why do we use oh, yeah. So maybe you can the question is that I just say white noise and did not specify any of the distributions, right? Distributions. Yeah, so you can still actually specify the distributions, but I know remember that the all these system ID properties is based actually properties are based on correlations and the power spectrums. They are all just depends on the correlations, and that's actually independent of the distribution. So more important is what happens here, and then after time tau second later, what you observed here, how they are correlated to each other. That's actually key point, rather than the whether here you have the nice normal distributions or gamma distribution, whatever. That's not so much an important issues. Yeah. So this is an interesting point. You can try out the different ones, but you get the very similar results. Yeah. So we don't care that the distribution, but randomness, white noise is a very key point. That excites the system very well. Okay, so rule of thumb, is that pick the random signals. That's your first preference. If it's not allowed, then you basically use some sharp signals, something that is more structured. Yeah. Okay, that's it. I hope you can solve this assignment problem without difficulty, spending not too much time. If And really bother you, please contact us. Yeah, I hope I can see the and respond to your questions. And okay, so you discuss it this Friday. Hope you can do it well. Okay, take care. Yeah. Oh, and this
Thank you.
Wednesday, there's no class, all right? And so you can relax a little bit. Yeah, yeah. And then we'll see you the next Monday. Take care. Bye.
Bye.
Bye.